progress.
Okay, today, let me see if the sharing is right first. Yeah, I think this is. I already uploaded the video of the last class. It's available in my USJ class feed for you to revise. What was dimensional analysis, the Buckingham theory, very important. It's so important to know these techniques because it helps you to identify which variables are relevant. You suspect the connection or correlation between some variables, and dimensionally you can know if there is some correlation between them. So that's quite good. And it's very simple. Once you get familiar with that theory, it's like so easy and enjoyable, right? We use that particularly people who study fluids, mechanics, or biological systems. Mostly they use these kind of techniques, but also I think, as I told you, if you do business or whatever, you can adapt the variables, corresponding variables, and apply the same techniques. I don't see so many people in business applying these things unless they are trained in mathematics or so. But it's good to learn these things anyway, because how good and how complex or how important is your research sometimes depends on the tools you may know. Then, of course, still in USJ, where we are a little bit kind with the students in the sense the defenses are very polite, very kind. But for example, I defended in Osaka, Japan, and it was five juries very aggressive, wanted to kill you in the and you had to defend, and sometimes the comments tend to be offensive actually. But this is the Japanese style, I think. This is how they they ask questions. When I went to National Taiwan University this Friday, there was a Japanese professor who I know very well. He's retired, and his questions were very. And then my friends, a few friends were shocked, but I was used to that. I just replied politely. But some people might interpret it bad, no? Because you are not used to that. I think here in USJ, people are more relaxed and you will not suffer this kind of issues. And only three juries. I think you only have one or two juries. I don't know how many juries you have. Okay. Yeah. So every university has different rules at the end of the day. So random variables, I think I mentioned this a little bit in the first class. Do you remember that? I told you that you could construct, somebody did this, but anyway, you could construct yourself a distribution. I told you many times that. And you can quantify things. And the example I put, which is the example because it reflects the behavior of our students, is the arrival on time to a place. And I told you I will write here a little bit before moving the I don't know if I should call it the slides or. Well, I told you can define a variable, and I can define the variable arrival time arrival to a class, and I could assign 0, 1, or 2, or more categories if I want, and I could say 0 for those who arrive late, 1 for those who arrive on time, just on time, and 2 for those who arrive very early. Who arrive very early today? Only you and let me remember the names. You are Yvonne, and she's Eve. You are Eve. Okay, yeah, because your name is more or less similar. That's why I could remember. So Yvonne, Eve, more or less like that. So then they should, for example, two students arrive very early. How many arrive on time? Let's put, how many are here? 3, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 18. So 18, 2 let's put 14 arrive on time and 2 also arrive late. Then of course I can assign a probability to each value. The probability of x equals 0 will be the positive cases, which is 2 to a student, divided by the total, which is 18. It will be 1/9. The probability of getting 1 is the probability of the students to arrive just on time. It will be 14 divided 18. This will be 7 divided 9. And finally, the probability of getting 2 is the probability of very early, which were again 2 students divided 18, 1/9. And this is my distribution. And I could plot this actually. I could plot probability and x. X is 0, 1, and 2. And it's some kind of histogram, for example. So 0 is 1. This will be 1/9. For the other, this, and for the other, something like this, around 2 or something like that. More or less. Let's put it like this. But there is no negative value, so more this part I will omit. But this is the idea. This is the 0, this is the 1, and this is the more or less. More or less. Of course, I painted it wrong because this area should be equal. These two areas are equal. Well, of course, I am not a good painter, but the point is that you can construct your histogram, your distribution, you can calculate the expectation value and the standard deviation of this. And there are standard ways to do it, and we will explain now in a moment. Then a random variable is nothing else than assigning a number to some quality. For example, the number of people, the probability of having people taller than 150 centimeters. You can assign a random variable to that. 1 if you are taller than 150, 0 if you are shorter than 150, and so on and so on. So let's go here for a moment. This is the case of a coin, for example. Tossing a coin, you put heads or tails, no? You can put the heads, but the value of head is 0, and the value of tail is 1. Then I can tell you what's the probability of getting 0, or the probability of getting 1. With one flip, yes, it's 50. Well, with many flips, it changes, no? It depends how many times you flip also. So this is just a basic example. So this is the sample of a dice, for example. You throw a dice, and let's define a random variable saying the score shown on the top face. So the score, of course, you know that is 1, 2, 3, 4, 5, or 6. So this is your sample space also. And then I can ask you the probability of x to be 1 is 1/6. The probability of getting 2 is 1/6. And everything is 1/6. If the dice is not somehow weighted toward one number. But I could change my random variable. I can say, okay, I don't want x to be the value of the top. I want to be, I will put this problem. I throw the dice twice, 2 times, not the musical group. I don't confuse because there's a Korean group called Twice. I am talking, you throw the dice twice, and then I ask, let's define the random variable x such that it means the summatory of the two, you define the sum of the two numbers with a random variable. Then it changed completely the scenario. Now it will not be from 1, 2, 3, 4, 5, 6. You can still assign arbitrary numbers to the results. But for example, the minimal value with 2 throws to two attempts is 2, no? Literally is 2, because you can get 1 and 1, or 1 and 2. So you have a different sample space. A different sample space, you can identify qualities, and you can define your random variable depending on which quality you want to explore. You will see that clearly subsequently. So in other words, you can define a random variable. Just you define the value, and this is the probability of that value. Throw a dice once, there is no mystery, it's 1/6. We already say that. The sum of probability is equal to 1. So now, let's do another example. Let's define x, number of heads is the random variable. We toss 3 coins. 3 coins, 1, 2, 3. And then somebody asks you define x to be the number of heads. So what are the possible values of x? In this case, if x defines the number of heads. Okay, let me get it here or bring it here. We say if I toss 1 coin, I obtain head or tail, 50-50, no? But now it's 3 coins. You flip 3 coins, they fell on the floor, and then I want to define a random variable such that x is the number of heads. So there might be 0 heads, 1 head, 2 heads, or 3 heads. Those are my options. What's the probability of getting 0 heads? For example, 0 heads. In that case, you have to construct the sample space, right? In the sense of random variables, the sample space is 0, 1, 2, 3, because you can have 0 heads. It means all was tail. Tail, tail, tail. 1 head means head. Yeah, the light, this light, right? Yeah. Whichever, I don't know which light is it. Okay, this. Okay, great. Yeah, this light is bothering me, the one. Let me see if this pointer, the pointer is working, okay. Yeah, I can use it. I mean, if it's tail, there are 0 heads, right? So you have 0. Probability of 0 is the probability of getting tail, tail, tail. Now, if there is only 1 head, it means it could be head, tail, tail, or tail, head, tail, or tail, tail, head. Right? That's it. And if it's 2, of course, it's head, head, tail, or head here in the first and the third, or and so on. So you have to distribute all the possibilities. And if it's 3 heads, of course, there is no other choice. There is only one event giving 3 heads, head, head, head. So depending on the number of events given each number, that will be proportional to the probability. So let's see what is the, here, look, sample space, here. Head, head, head. The random variable is 3 because the random variable measures the number of heads. Head, head, tail, 2. Head, tail, head is also 2. And this is also 2. And how many possibilities we are? 8. 1, 2, 3, 4, 5, 6, 7. And the last one is this one, 8. Then I want to know something. I want to calculate the probability that x is equal to 3. What do you do? X equal 3. What does it mean x equal 3 here? X. Remember, x is number of heads. There are 3 coins. 1, 2, 3. So when x is equal 3, when it's equal 3, it means that this is head, head, head. What's the probability of getting x equal 3? X equal 3 is this. Head, head, head. There are 8 possible options, 8 possibilities. So the probability of getting x equal 3, there is only one option for getting all heads, divided by all the options. Yeah, this is the probability of getting all heads. The same will be for 0, because 0 is tail. 0 will be tail, 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 and this is 0. This is 3. It will be also 1/8. But what if I ask you equal to? What? How do you get it? Let's count it. I think probably you're right. But let's do it slowly. We are slow persons. No, no. I'm joking. No, it's okay. But what I mean is that, yeah, she's right. She's right because there are 3 positive events giving 2. 2 heads here is 2. 2 heads here is 2. And it's only 3. 1, 2, 3. 3 divided 8. So at the end, this is 3 divided 8. There is something missed? Yes. Probability of x equal 1. Is equal to what? Let's count the possibilities. 1, 2, and 3. So again, it's 3/8. And let's see if we did a mistake. The summatory of all these probabilities should be 1. 1 plus 1, 2, plus 6 is 8. 8 divided 8 is 1. So I give 1. Right? So it means this is our distribution. And now we can calculate expectation value and standard deviation. In advance, I can tell you that the expectation value of this random, in these cases, is simply a weighted average. Are you familiar with weighted average? Average with some weights, which each number in the average has some weight, and some numbers are heavier than others. That's the meaning. You use that in many applications. You use that for constructions. You use that for finding the center of mass of a body, center of gravity of a body, and that's what the engineers use for constructing bridges or whatever. And you use in biosystems, biological systems, and even in business you use that. In many applications in business. So I was surprised if you don't use that in business. Well, an expectation value of this random variable, it will be just the sum of each value multiplied by its probability. This is more or less you will see that it means that I take, for example, 0. Well, 0 multiplied for whatever is 0. Well, I will put it multiply 1/8 plus 1 multiply 3/8 plus blah 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 blah. At the end, the summatory of these things give you expectation value. But let's go slowly because that's after. So this is the values we found just now. 1/8, 1, 3/8, 3/8. Okay. Now 2 dices. Wait, this doesn't behave so well, so I can define another random variable for 2 dices. The sum of the scores of the 2 dice. Yeah, I knew that we'll do this example actually somehow. So you can put the possible values 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 2 is the minimal, and these are all the possible values you can get when you throw 2 dice. There are 36 possible outcomes, and this is the sample space. Well, x is the sum of the score, so this is the value of x. Then probability of x2, x equal 3, x equal 4, blah, blah, you can calculate. So you can, for example, 2 occurs only once, so probability of x2 is 1 divided 36 because there are 36 different options. 3, the combinations 3 give 2 options only. The combination 4 gives 3 options. 5 gives 4 options. 6, 5 options, and so on and so on. Now, if I ask you here, what is the probability of x equals 0? Zero. What is the probability of x equal 1? Zero also. But there is no way to obtain 1. So the probability of x1 is 0. And let me see. Los tres probability of getting x equal 13, also 0. Whatever doesn't appear in the sample space has 0 probability. So it was some kind of cheating question. Because sometimes in the exam I ask these questions, especially bachelor students, and then they calculate something. And then I'm thinking, no, it's 0. Why they do that? I don't know. So now we can also calculate the range of values. You can see that in discrete, this is discrete random variables. What does it mean discrete? Discretization. Discrete. Discrete. What does it mean? That there is from 1 to jump to 2, from 2 you go to 3, 4, 5, 6. There is no 0.5 or there is no 1.3. There are no decimals. All the numbers are integers, integer numbers. So there is a finite number, and well-defined probability for each number. For each number. This is important because when you jump to continuous random variables, the situation changes completely. In any case, we can also calculate the range of values. For example, this is an example between 5 to 8. What is the probability that the sum of the scores is 5, blah, blah, blah? Then you calculate the probability 5 plus 6 plus 7 plus 8. This is the example with the 2 dices, no? And at the end, you obtain a number. Now, if you sum all the probabilities, if I have 9, 10, 11, 12, and 4, 3, 2, I should obtain 1. If I sum all the probabilities. So in other words, if I do this, x 2, 3, until 12, this is 1. Because it is sum all the probabilities. But here is only between 5 to 8. 5 to 8 what? What we're talking about here. 5 to 8. So 5 is here. 6, 7, 8. From 5 to 8 is 5, 6, 7, 8. 5, 6, 7, 8. Okay? Great. So there are some issues. If I have a continuous random variable, I cannot assign I have a probability distribution here. I will call it rho. Let's assume it's something like this. If I ask you in a continuous distribution, the probability of x equal 3, what's the result? In continuous, in discrete, there is some value, no? But now it's a continuous random variable. What's the result? It's 0. It's 0. No matter which number I select, probability of 4, 3, or 2, is 0. And what's the reason why it's 0? Because there are infinite numbers. Because it's a continuous variable. Between 0 and 2, there are infinite amount of numbers. Between 2 and 3, there are infinite amount of numbers. Just study that in primary and high school, no? There are, because there is 3.1, 3.2, 3.3, and also 3.00001. So there is technically infinite amount of possibilities. So since there are so many infinite amount of possibilities between two numbers, whichever they are, the probability of getting a sharp number, sharply that number is 0. in continuous probability distribution, you can only obtain probability of range of values. The probability between 3 and 4, or the probability between 0 and 2, these kind of probabilities. Okay? But you cannot define punctual probabilities. So that's very important. Okay, now we have the basic notions. If there is time in this class, I will ask you to design your own distribution based on some variables related to your research. Invent variables. Invent variables for your research. So now let's go. Let's close this guy here. Well, I can technically just open here. Let's go here. Now we will define formally mean, variance, and standard deviation. What is the relation between variance and standard deviation? What is variance? Variance and standard deviation, what does it measure? Do you remember in basic probability theory, the mean value measures the center of the distribution, no? The center. And the standard deviation measures how much it is spread around the center, the distribution. The data is spread around the center. If the standard deviation is 0, what will happen? You will have a delta Dirac actually. It's a delta Dirac distribution, but it's a sharply, only one number. That's not a probability anymore. It's sharply that number. No? So, and variance and standard deviation are related, of course. One is the square of the other. We will see that in a moment. Then let's go here. This is the same example as before. Down. This is the definition of mean value, is what I wrote in the board. You sum all the possible x and multiply by the probability. For example, here, for the dice, 1, 2, 3, 4, 5, 6, each one with some probability. Well, this is some kind of weighted dice, no? Because they don't have the same probability. So at the end, you calculate the product of x, the random variable with the probability, the product, and you obtain something and you sum these values. When you sum these values, you obtain the mean value, the expected value. I think probably it's a weighted dice. They say it's cheating. So you have these probabilities. This is a weighted dice because the probability of 1 is not 1/6. It's smaller than that. The same for this number, but this number has a very high probability, the number 6. The probability is 0.5. So most of the attempts, 50% will get 6, and 50% will get all the other values. So that's a weighted dice. So somebody put something to the dice for it to be almost 6 the whole time. And then you can calculate the expectation value. You have 1, 2, 3, 4, 5, 6 with the corresponding probabilities. You calculate the product of p with x. 0.1 times 1, 0.1 times 2 is 0.2. 0.1 times 3, 0.3. 0.1 times 4, 0.4. 0.1 times 5, 0.5. And 0.5 times 6 is 3, because it's a multiplier by 1/2. You sum this plus this plus this plus this plus this. This is the mean value, actually, expectation value. 4.5 is this guy. So this shows something. The mean value is not 3 as we expected, or 3.5 as we should expect in a normal dice. In this case, it's 4.5, so it's around here, the mean value. The variance is the sum of the deviations, of the square of the deviations with respect to the mean value. You have the mean value already. You elevate to the square, for example, 4.5 to the square is this, and you subtract that value by the summatory of the square times p. Of course, nowadays we have software who do these things for us, but it's important for you conceptually to understand what is this. Again, let's calculate. You have x, 1, 2, 3, 4, 5, 6, the probabilities, and now calculate the product x squared times p, and you get these numbers. You sum these, and then you have this quantity. This minus the mean, which you calculated, 4.5 squared, gives you the variance. What does it measure the variance? It measures how much this data is spread around the mean value. Yeah? The variance is 3.25. Standard deviation is the root square of the variance. You calculate the variance, 3.25, and you calculate the root square, and that's it's plus minus. Plus minus is because it distributes from both sides, right? To the right and to the left. Yeah, that's the reason why it's plus minus. This is another example. You plan to open a new blah, 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 and found these statistics for blah, blah. 20% earning per years, 30%, 40%, tan. Using the probabilities for your new restaurant profit, what is the expected value and standard deviation? Of course, you are using the historical for opening the restaurant. You are using the historical data of previous restaurants which were successful or failed. And this was the percentage related to what they are. And then you can calculate, of course, well, this jump too drastic. You can define the random variable to be possible profit. And then you define this table here. 20% is 0.2, 30%, 40%, 10%, no? Earnings, they omitted 3 zeros. There is a way to, I mean, you can standardize this. You can delete zeros if you want, just for making it simpler. This guy, there was a loss here, zero income, and this is positive income. Then you multiply XP. This is for calculating the mean value, the summatory of XP. X is the random variable multiplied by the probability. 50 times 0.2 is 10. 0.3 times 0 is 0. 0.4 times 50 is this. 0.1 times 150 is this. You sum this. Expectation value, 25. And the standard deviation, you need to calculate this, x squared p. This square times 0.2 is this. This square times 0.3 is 0. 50 squared times 0.4 is this, blah, blah. You sum this. You have the ingredients for calculating the variance. Will be this value minus this value. And then you obtain this variance. And this is the standard deviation. These are thousands of dollars because they omitted 3 zeros, though the expectation value is 25,000 US dollar. And the standard deviation is 56,000 US dollar. This is the profit you might expect, 25,000 US dollar. I noticed that in Macau, not only in Macau, everywhere people open business without doing serious, you call it marketing or marketing, no, revenue analysis, no? Business, financial analysis, no serious financial analysis. So when you don't do it and you are just blindly doing this, the chances for getting broken are quite high. So that's why many business, coffee shops, whatever, they open, and then you show 2-3 months after they disappear. Because these guys, they didn't do a serious study. Also the location of the place, no? Especially many people after COVID-19, they failed. It's because the consumption behavior changed, and then they were opening business based on the knowledge before COVID, no? But after, people changed the habits of consumption also after COVID. That was one factor. Another issue is the location. Some people try to locate luxurious brands for people to buy luxurious brands in San Malo. I think it's a bad location for that. San Malo is not for luxurious brands, no? There is also a technical analysis for that. I mean, where to locate the shops, depending on normally a safe way to play is you analyze, there are many Starbucks and Pacific Coffee or whatever here in this area. So it means this is a good spot for a coffee shop. Some people play like that. If there are many shops here, it means that here people consume a lot of coffee. Well, this is just a parenthesis, but it's part of the research of many people. No? So my point is that take serious, especially those guys who are in business, because I know a scientist in biology, in engineering or whatever, they take serious. But I have seen the tendency, and more tendency for business people to get phobia to math or to quantitative analysis. But actually, that's what guarantees you success in the business. Actually. Because you cannot go jabba dabba do like the Flintstones to do business, no? You need some numbers, you need some facts. Then, okay, example. Now, so now you know how to calculate expectation value of variance. After, in the second half of the class, probably I will ask you to do it. Remember, the mean value is calculated like this. This is a weighted average. Is the summatory of each value of the random variable multiplied by the probability. Let's do it for the coins, for example. Do you remember the example of the coins? Head, tail. For head was 1/8, right? So it means, in that case, when you calculate the expectation value, in the case of the 3 points, 1, 2, 3, for x equal 3, which is head, 3 multiplied by 1/8 plus 2 multiplied with whatever is the probability of that, which I forgot already, but you can remember later. 3/8, right? 1, 3/8 also, I think. And the other is 0, but 0 doesn't contribute to anything, but let's write. 0 means tail. And this is the expectation value. At the end, I can assume is 3/8 plus 6/8 plus 3/8. And this is what? 6 12 divided 8, which is 6, 4, 3, 2. 3 divided 2, which is 1.5. 1.5. These are small numbers. You don't need a calculator for that. I think you spend more time using the calculator than doing like that. Then, now, and for variance is simple. You already have the expectation value here. It will be 1.5 squared here, and you can just calculate this part. And this part, how do you calculate here? It will be this summatory of x squared p is 3 squared multiplied 1/8 plus 2 squared 3/8 plus 1 squared 3/8 plus 0 squared 1/8. This is 0. 1 squared is 1, 2 squared is 4, 3 squared is 9. And then you sum, and whatever the result is minus 1.5 is the variance. And the standard deviation is just the root square. So this is a basic distribution and this distribution might be important for your case because in most of the cases you are analyzing, maybe you will not have a huge population. Maybe you will do a survey of just a few people or whatever. I don't know what kind of research you do. Maybe you are inventing your own random variable. Let's assume your research is fashion or fashion taste. I'm not a fashion person, but let's assume because some people, I think we have a faculty here of what arts and something, and I'm sure that somebody must be doing that. Then even in fashion, you can define a random variable. Assigning any quality to the dresses, no matter, for example, short, long, or whatever, classic, not classic, blah. You can define your random variable arbitrarily. Or black dresses, white dresses, right? You put a number to each color, for example, to analyze the taste, and you can create your distribution to see how many people like black color, how many people like green color, how many people like, and then you make your distribution with that. So there are many things, infinite amount of possibilities you can do. And in any research field, it's not close to, it's not only for a scientific or for, well, everything technical is a scientific, but let's assume the standard notion of a scientist, which we portray, which is physics, math, and engineering, no? And maybe biological science. The other fields also do a science somehow. They do a science, but it's a different kind of a science. Finance is some kind of a science for me. Then, okay, now you are done. You are done with random variables, discrete, and so on. Now it's 7:55, so still we have time. Let's go here. I think we did that the last time, so I will not talk about this. I will jump directly to the normal distribution. Well, before the normal distribution, I must come back to this part. Let me delete, close this one. Covariance. Covariance. And then for covariance, let me see which screen is moving. Yeah, covariance. We talked about this the last, I think the first class we talked about covariance. In statistics, when you define random variables, because there might be more than one random variable in your problem. When we saw, and you can combine all these skills, for example, you can use statistics, you can plot the data, you can analyze the data statistically, and you can find expressions compact via dimensional analysis, for example. But for two variables to be functionally related, there must be a positive or negative covariance between them. If there is no covariance, if the covariance is zero, there is no correlation between them. This is an example of negative covariance. When one variable increases, the other decreases. This is positive covariance. And this, well, it's not working, the control. Let me see. Okay, now it's working. So, for example, let's go to an example and you will understand. Ice cream sales. The local ice cream shop keeps track of how much ice cream they sell versus temperature on the day. There are two variables here. What are the variables? The amount of ice cream you sell, and the other variable is the temperature. What do you think will happen if the temperature increase? More people will buy ice cream or cold drinks. You will not order a cafe latte in the middle of 35 degrees or 40 degrees in the sun. I'll give me a cafe latte, no. Hot, no. Macchiato, no. You will ask ice, no? Or ice cream or whatever. So the larger the temperature, you should expect more ice cream sellings. Look, this is what happened here, two variables. And you can analyze with that data collected. Once you collect the data, you can analyze the mean value for X, but also the mean value for the other variable. Mean value for temperature, there are 1, 2, 3, 4, 5. So this is not a weighted average, it's a simple average. Mean value 1, 2, 3, 4, 5 divided 5. And this is 1, 2, 3, 4, 5 divided 5. So the mean value of X, mean value is Y. And then for each pair of values, you can subtract the mean value. And then you can sum this, and it gives you the covariance. So it means, look at this, 17.12 is here. And 345 is here, but it's also here, 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 here. And these are the individual values temperatures: 14.2, 16.4, 15.2, 22.6, 17.2. And the same happened with these values of Y: 215, 325. These covariance some software can calculate, of course, but I want you to understand the concept. You multiply the difference between the temperature minus its mean value, multiplied by the salines minus the mean value. For each value of saline corresponding to each value of temperature, in agreement with the table you saw here. And then at the end, this superposition of these numbers divided, in this case 5 minus 1, gives you the correlation. Minus 1, well, minus 1 is when you, technically is when you sample, no? It's like when you are not sure about the population, you subtract the 1, but we are used to divide by 1 when it's the whole thing. But when it's a sample, we are not sure, then people subtract the 1. So this is the general formula of covariance. This is the summatory of the individuals' values minus the mean value of the first value, product the second variable minus the mean value. You sum all the possibilities and divide by the number of pairs correlated minus 1. What happens if this value is 0? What happens if this is 0? For example, it means the change of temperature doesn't affect the salines. It means that it will be a lie that the higher the temperature, more salines of ice cream. There will be a big lie. That could happen. That doesn't mean there is no correlation sometimes. Sometimes it's because you are looking at it wrong. For example, if you locate your shop is hidden. Somehow nobody sees it. So everybody bypass it. Even if it's hot, they will not go to buy it. So I think you have to understand that also there is another variable, the location. The location is a third variable, and there might be as many other variables as you wish. And they might be correlated in pairs, each one. And at the end, there is a single expression, which you can obtain via dimensional analysis, which is what we did the last time. But here, for simplicity, only 2 variables. But it's quite obvious that the larger the temperature, the higher the salines. That's why the correlation is positive. Now, this 243 doesn't tell me so much. It doesn't tell me so much because 243 what? Dollars, yeah, nice. But it doesn't tell me what's the dimension of this correlation. How strong is this correlation? For knowing how strong is the correlation, it's better to normalize this quantity. So that's why we have the coefficient of correlation, which goes from -1 to 1. So this, later we will see how to calculate. But once you have this, it's very trivial to calculate. But, well, let's write here. Obviously, if this is positive, but there is something called coefficient of correlation, which is -1 to 1. If it's 0, no correlation. If it's 1, maximal correlation. If it's -1, maximal negative correlation. Still, even if it's negative, there is a perfect correlation if it's -1. Examples: positive correlation in this. This is positive correlation. Negative correlation, this. Negative correlation. And no correlation will be this changes, but the other doesn't change. Or vice versa, or vertical. This or this are no correlation. Okay? Well, actually they divide, they explain why no x and -1. So anyway, let me show you something else about correlation. I will share with you a textbook. This textbook is very nice. It's for business, but it has some mistakes. Actually, if you see through the textbook has some typos, serious typos. I don't know how good it is to share with you a textbook with typos, but or I might share another one. Let's go here. It's not moving. Let me see. Are you moving? No. They should be here. Share. But anyway, I have to trust. This is what I was talking to you. Coefficient of correlation. Or they call it variation or covariance or whatever. People call it differently. This 200 something you saw, that number is this, the numerator, the 243 or something we calculated. And then you divide by the root squared of the variance, so a standard deviation of x, product standard deviation of y, so you have to calculate the standard deviations of each of the random variables involved, a standard deviation of the temperature, the standard deviation of the ceilings, introduce it, and you obtain rho will be between -1 and 1. In this case, since it's positive, will be between 0 and 1. And since we expect this correlation to be strong, we should expect it to be close to 1. Close to 1. If it's 0.1 or so, you can start to suspect something strange, no? This covariance has some alternative formulas. This is the alternative formula of covariance, which is the expectation value of the product xy minus the expectation value of each one of the random variables involved. Expectation value of temperature, expectation value of settings, for example, in the example before. And this expectation value is you have to multiply individually each couple of variables and multiply by the corresponding weights. So anyway, I will send you some samples later about this. I think they do some examples here in this textbook, but we will analyze right now because I think with the examples provided before are enough. But later I will share with you this textbook and you will be able to see. So this closes discrete random variables right now. By the end of the session, I might ask you to analyze one of these solutions. They are solved. Those problems are solved. You only have to analyze them. So when they give you a solved problem and you study it step by step, and you, they do, why they do this? You start to understand, right? What is the success of the human race? This is a crazy question. What is the success of the human race? Why we are so successful with respect to other species? Why do you think the humans, we developed so much? Why the monkeys didn't do, or why the tigers don't do that? It sounds a stupid question. It's silly, but because we can transmit information to the next generation. They don't have to start from zero. Okay, that's the success of the human race. So what you're doing here is to watch what others solve and then you repeat. Okay? So that guarantee, for example, in the oceans, those guys who are biologists or whatever, the killer whale is the king of the oceans, no? Killer whale. It's not the shark at all. Why a killer whale can defeat a shark? Because they transmit information to the next generation. They tell how to kill a shark to the go. These sharks, a smaller brain, they don't communicate each other, very individual. They cannot do so much. In our case, of course, it's a higher degree of development. But this is just a parenthesis. So what I'm trying to say is that we will see examples which were solved by somebody else at the end of the class, I can display them here, and I will ask you to think about it 10 minutes or so, and then you will try to solve it. And then somebody will come here, and that's participation. So this closes the discrete random variables. Now let's go to continuous random variables. Let me close this guy here. Or let me bring here. Random variables continuous. Yeah, for this random variables continuous, this is the example of the past. This is discrete. This is a basic example of a continuous random variable. This one. The probability of getting each one of the the probability of getting something between A and B is 1 divided B minus A. Here, the density of probability. So the area of this rectangle is 1. If you multiply A minus B for this, you will get 1. So this is telling you in a continuous random variable distribution, the total sum of probabilities is measured by the area below the curve of the distribution. The area here is 1. Okay? Area of the rectangle is 1. This is one simple one. But if I ask you, wait, this doesn't move. Let me see. Okay. Who is the guy of the telephone? -1. This is an example. All faithful erupts every 91 minutes. You arrive there random and wait for 20 minutes. You just wait for 20 minutes. What is the probability you will see it erupt? 20 minutes of 2 decimal, blah. Well, they do this distribution. They put P 1 divided 91 is the difference between this point and this point, right? So this is just figurative. I will send you this thing solved, but the total area of this is 1, and this small shadow is 22%. It measures 22%. Okay? You can calculate this area actually. This minus this is 20. I multiply by this, which is the vertical length. 20 divided 91 is 0.22. This is just an arbitrary example. They designed this distribution. It's not really rigorous. Now, there is something called cumulative distribution. Cumulative distribution is the sum of probabilities between one point to the, for example, if I put this 3, x equal 3 here, is the probability between 0 and 3 continuously. Is the area below the curve between 0 and 3. Here, for example. Let's put it this way for you to understand it better. And I think when we go to normal distribution, you will understand it better. The only continuous distribution I will teach today is the normal distribution. So in normal distribution, you will have this. Like this. Then cumulative distribution is telling you is the probability between one point to the variable, to the value you want. For example, if this is 3, you will be on to 3. And internally, the density of probability Well, you don't have to calculate this integral. You don't have to worry about that. People already did it. And we just take the results. But this is the formal definition. Then, for example, here, cumulative distribution will be this area here between A and some value of X, which is defined. You will understand this better with the normal distribution. This is the normal distribution. We will see it in more detail. A standard normal distribution, it has zero mean value. The mean value is zero, and the standard deviation is 1. The standard deviation is 1. Well, the variance is 1. The standard deviation is plus minus 1. Let's put it that way. And this is important for, understanding this distribution is important for knowing how to do estimation theory. Otherwise, we cannot do it. Then let's go here. Again, the area below this curve, this area is 1. The area below this curve. And this area here, this is a small area, this little area, is a measure of probability between 0 and, in this case, 0.45. Between 0 and 0.45 is this. But you cannot say, I want to know the probability of getting 1 is 0. Probability of getting 2 is 0, etc. For understanding more formally this, I will go to the textbook. And I will come back to some other, this is the textbook, right? So let me share the textbook. Share. Let's go to the normal distribution here. I have to go here. Normal distribution. This one, yeah. You. Here. Normal distribution. This is great. This is the density function, the density of probability. This is the standard normal distribution, 0 expectation value, and as you saw before. And this quantity is because I want you to understand what is cumulative distribution. The probability between A and B of any random variable for a continuous normal distribution is the integral between A and B, the summatory, you have to sum, the density of probability. So it means it's the area of the curve between A and B. So let's put it A here and B here. The area, this area is the probability of getting, and is the integral between A and B of some function here, dx. Fortunately, you don't have to calculate this. Fortunately, because people already did it. Then, let me see. I want to move softer. If I integrate from minus infinity to infinity, I am covering the whole curve. So it gives me 1 because this means the total probability is equal to 1. So the area of this curve is 1. Okay? And this guy here is what we were talking about. It's the cumulative distribution. It's related to the cumulative. Is this G of C, this is how they standardize the normal distribution, is from here, from minus infinity, means from the end of the curve until some fixed value, which I can define arbitrarily. This area is defined by G of C. This G of C function. And the tables, which we will see in a moment, the tables for defining the probability of in this kind of distribution are standardized with this function, GOC, which goes from here to here. So you can derive any probability just by knowing GOC. We will see examples also. I will put you to analyze examples because in this way it looks very abstract right now. So for you, probably. Which will be the second part of the class. You should know this is GOC, this area. And this is the complement actually. G of minus C is the complement. It's this small area which is equal to this small area. So if you sum this plus this small area which is G of minus C, you get 1. So you can play with this. So there are examples here we will see in a moment for a standard normal distribution. When you go to the software, that will be in 2 classes or 2 sessions. You will see how to calculate this with the software in a simple way. The software normally, you have to specify if it's a standard normal distribution or normal distribution. What's the difference? Because the standard normal distribution has 0 expectation value and variance equal 1. But and this is the standard one, but any normal distribution could be with a different expectation value. So let's put it this way. The standard normal distribution has expectation value 0 and variance equal 1. But I could have a distribution where my expectation value is 20 and my variance is 400. So I cannot use the same equipment here. I cannot use this G of C. These things, I cannot use it anymore. There are 2 ways to attack this problem when it's like that. One, I can convert this to the standard case. There are ways to do it, which is the handwriting way to do it. But a simple way is you specify to the software that part. Some software, if you don't specify the variance, they assume that it's 1. In some software, actually the software I use normally is like that. In others, if you specify this number, then the software immediately understands, there is a variance different, etc. If you don't write in the same way, you don't write expectation value, the software will assume expectation value 0. But if you specify expectation value, then it will understand that it's not the standard normal distribution, but a different normal distribution. Which is related, it's just shifting the curve. It's the same curve, only that you shifted it. You shifted to a different value. So it's exactly the same curve. Later, I will ask you to make examples, to see examples solved and so on. For normal distribution, we have expectation value here also. We have variance. The expectation value of the standard normal distribution is 0. The variance is 1. We already mentioned that. And of course, this is the case when the normal distribution is not the standard case. There is an expectation value finite, and there is a variance. Now let's go here. Look at these two distributions. They are both normal distributions, but what is the difference between both? I will ask a few questions here. What is the area below this curve? The blue one. The total area. 1. The total probability. And what is the area below the curve of the yellow one? Also 1. But then what's the difference between this blue curve and the other? They have the same mean value, huh? It's 2. So what's the difference between both? 1 each more than the other. Well, what does it mean? The standard deviation, right? The standard deviation of the blue one is larger than the standard deviation of the yellow one. So you see these two, you know that for the case of the yellow, the data has the tendency to distribute more around 2. in a more fair way than in the case of the blue curve. In the blue curve, the data is more spread everywhere. It's around 2, but it's still wider. It can appear very far away from 2. But this one, if your experiment depends on being around 2, that you trust the experiment because the value has to be around 2, I will trust more in the yellow one than in the blue one, for example. This is a way to. This is basic statistics, of course. This is what I was talking about. You can shift the curve. These two curves are the same standard deviation, but different mean value. This is 2 and this is 5. And both of them can be converted to the standard normal distribution, which is what they do here. They explain here in this part. You can convert by defining a value, a new variable C, where you put the mean value, the standard deviation, and you convert again to the original distribution, a standard. And then this standard distribution is what appears in the tables, what we can see. We can calculate it by hand. And then afterward, you convert it back to the variables of the original problem. But of course, doing that will be too complicated for many people. But it's my obligation to tell you that this is possible to be done. Excellent. Later, we will see some. This finished the part of continuous variable distribution, which is a little bit more complex. And I want to close this part before the break with this, a standard normal distribution. Now, there are some distributions I didn't mention. Hypergeometric, Poisson distribution, binomial distributions. Those are very important and I think could be relevant for certain experiments. I think I will mention them briefly next class, probably, but I will ask you as a homework to investigate about it. You will investigate those 3 distributions. Copy. Binomial distribution, hypergeometric distribution, and binomial distribution. Binomial, as the name says, is 2 options, positive or negative. Hypergeometric is when you select the Poisson, you select a sample when there's a huge amount of population where you select a small sample, and when the probabilities are quite low. The probabilities of what you determine to be successful. What is success in the sense of random variables? When you define a random variable, for example, the random variable is number of black shoes. What I define as success in that experiment is when I see a black shoe. That's success. So the term success in the sense of probability is not the success of winning or so. It's what you consider is the positive output of the experiment or the quality you want to extract from the experiment. This is the standard normal distribution, guys. Let me see if I am sharing the right screen. This is the standard normal distribution. This is an example. You can see that it's standardized. This C is what you saw before, the G of C. I think you forgot a bit where I will explain. The G of C was minus infinity to some value of the, well, this is in the tables. You can find this tabulated in tables. Then when C is 1, for example, immediately this gives you some value. It gives you the value of G of C, which is the area from here to here. So here, as you can see, the system is giving us immediately the probability. So actually, you use this website, you don't have to do anything. For any value of C, you can find what's the probability. 47, etc. And of course, this is a mirror image. So the same you find on the right-hand side is the same on the left-hand side. This is the table for C, actually. When C is 0.1, 0.2, 0.3, 0.4, if it's 0.51, you have to go here, for example. this one, a C of 0.51 here. So I mean, this table tells you what is the value, the area between the lowest point toward the point of interest. Let's put it this way. This is a standard normal distribution. I want to put C equal 0.51. Then I go to this table. 0.51. Because 0.01 is attaching 1 here. Then it's giving me 0.1950, right? 0.1950. So this 0.1950 is the area between this point to here, which actually 0.51 should be lower, but it's this area. It's this area between here to this point. And the same with the others. Okay? 1.23 here. But at the end, of course, you will say, well, I can do that with the software. Yeah, you can do it, but I want you to understand right now this thing more or less. So this part, of course, it was taught in rush because, of course, we don't have enough time for anything. But I think you have at least a basic notion right now. I will stop sharing here. You have a basic notion of what is a random variable, how to design a random variable based on the experiments you want to perform, discrete random variables, how to calculate probabilities in that case, how to define distributions. And now when you go to continuous, which is the case of the normal distribution, you more or less know. For this continuous case, I think it's a little bit more difficult for you. It's a little bit more difficult. But in the second part of the class, I will ask you to analyze some examples which will clarify to you how to use this distribution. Because I will tell you a news, many systems in the nature and in business and whatever follow the normal distribution. So this distribution is very important. It's very, very well used everywhere, especially when you have millions and a huge amount of data or so. Then I will stop this recording now. Let me see.